Hello friends, welcome back to my channel. I hope you are watching my videos. This is fourth part of my lecture series on distillation. In the first part I have discussed fundamentals of distillation. In the second part I have talked about material balance for distillation. And in the third part I had started my discussion on vapor liquid equilibrium. In fourth part, which is fourth part in the lecture series, I'm going to continue my discussion on vapor liquid equilibrium. For those who have missed my previous lecture, I'm giving link to that lecture in the description section. You please watch it and please do subscribe to my channel and hit the bell icon. Okay, so this is distillation part 4, and this is again we are going to discuss vapor liquid equilibrium in this part. So let us start the discussion. Vapor liquid equilibrium, that is VLE. In our previous lecture we have understood vapor liquid equilibrium for how to represent VLE for pure components, and then how to represent it for a binary system. For that we had considered a binary mixture of A and B, and out of these two components A is the more volatile component. Okay, so VLE for the simple binary mixture is represented on a three-dimensional plot like this. Okay, so you have pressure, mole fraction, that is composition, and temperature. Three variables come into picture, and that is why you have a three-dimensional plot. Okay, well, you please watch my previous lecture to understand the concept. I have discussed it over there. Okay, shortly we have vapor pressure curve for pure B, which starts from CB and CB, which is the critical point of B, and it extends to TPB, which is triple point of B. And this curve, vapor pressure curve for pure B, it is lying in x is equal to 0 plane. Okay, and that for A, the vapor pressure curve for A, it extends from CA, the critical point, to TPA, the triple point for pure A. And that vapor pressure curve, it lies in x is equal to 1 plane. Okay, so it is difficult, it is somewhat difficult to understand really on this three-dimensional plot. Okay, so you can understand it in a better way. The VLE, it can be understood in a better way if you either study it at constant pressure or you study at constant temperature. Okay, so if you are studying it at constant pressure, that means out of the three variables, one is kept constant. So now this will be a constant and you will have only two variables. So when you are studying at constant pressure, you have two variables, temperature and composition. And when you are studying at constant temperature, again you have two variables, pressure and composition. Okay, so if you do this, if one of the variable is constant, either pressure or temperature is kept constant, then you can understand really in a better way. Okay, so accordingly we have constant pressure equilibria. If you study VLE at constant pressure, you have constant pressure equilibria, and if you study VLE at constant temperature, you have constant temperature equilibria. Okay, so you have constant pressure equilibria and constant temperature equilibria, and in this lecture we are going to understand constant pressure equilibrium. Okay, so let us understand constant pressure equilibrium. Again we will start with the same three-dimensional plot, and let us see how it gets simplified if you are studying BLE at constant pressure. Okay, so let us understand. Constant pressure equilibria is represented by the loop curve, constant pressure equilibria that we are talking about. It is represented by the loop curve. What is this loop curve? This loop curve is produced through the intersection of constant pressure plane and the double surface. Okay? So if you remember, in this three-dimensional plot, area between the two planes, which two planes? X is equal to 0 plane and x is equal to 1 plane. You have a double surface between the two planes. X is equal to 1 plane, that is this plane, and x is equal to 1 plane, that is this plane. You have a double surface, and that double surface extends from vapor pressure curve for pure B to vapor pressure curve for pure A. Okay? So if you are using a constant pressure plane to cut that double surface, okay, so intersection of that plane with the double surface, it produces a loop curve. We have already understood it in our previous lecture. Okay, so the loop curve, it is produced through intersection of the constant pressure plane with the double surface. So I'm showing that plane. So this is constant pressure plane, a plane parallel to temperature axis, constant pressure plane, and it is cutting the double surface. Okay, so that intersection occurs, or that intersection produces this loop curve. Okay, that's why we are saying constant pressure equilibria is represented by the loop curve that is produced through intersection of constant pressure plane and the double surface. And the loop curve that we are talking about, it extends from TB to TA, where TB is boiling point of pure B and TA is boiling point of pure A. Okay, so the loop curve that is formed, it is extending from boiling point of pure B to boiling point of pure A. Okay, so from TB to TA. So in this case, TA is boiling point of A and TB is boiling point of B. Okay, so constant pressure equilibria is represented by this loop curve. Okay, now let us move. Okay, so this is the loop curve that represents constant pressure equilibrium. Okay, now what we will do, we will see how this loop curve uh, looks like when you remove all other parameters. Okay, so let us see. So now I have erased those curves. Now you can see you have a constant pressure plane, and now you are seeing the double surface that is obtained through the intersection of this constant pressure plane with the double surface. Okay, now this further uh, we will have temperature axis over here, then we will have composition axis over here, and then again you have temperature axis over here. Okay, so the loop curve now is seen on a two-dimensional plot. Why I am calling two-dimensional plot? Because now you just have two variables. One is temperature and the other one is composition, that is mole fraction. Okay, so therefore we need two axes. One is temperature axis and the other one is composition axis. Okay, so again I will make it simple. Now let us instead of having it in a slanting position, let us move it like this. So this is the temperature axis, this is the composition axis, again this is the temperature axis, and the loop curve will be looking like this. Okay, so now you see a loop curve on a two-dimensional plot where there are only two variables, temperature and composition, and this loop curve is extending from boiling point of pure B to boiling point of pure A. Okay, now let us draw it in a proper way. Let us represent this loop curve in a proper way, and then we will understand that. Okay, so you have temperature plotted on one axis and mole fraction plotted on the other axis. So one end represents x is equal to 0, that is pure B. If you remember, x was mole fraction of more volatile component, which is A. So if it is 0, that means it is representing pure B. And if it is 1, then it is representing pure A. X is equal to 1. There is only one component, and that component is A. And over here, x is equal to 0, and it is representing pure B, only one component, that is B. Okay, and then you have boiling point of pure B and boiling point of pure A, and the loop curve is extending between those two boiling points. Okay, so the loop curve now, which is constant pressure equilibrium, it is extending from boiling point of pure B to boiling point of pure A. Okay, now let us understand this in details. This diagram is representing constant pressure equilibrium. Okay, so let us move on. Now, in this, you already know small x is the mole fraction of A in the liquid. A is the more volatile component. Y is the mole fraction of A in the vapor. A is the more volatile component. I already told you. The lower curve, I'm talking about this curve. The lower curve. What is this? It is a plot of x versus t. If you plot mole fraction of A in the liquid phase against corresponding temperature, you get the lower curve. We will know it in more details shortly. So for time being, let us understand that a lower curve is obtained if you plot x versus t. X versus t. So this lower curve is x versus t. Then the upper curve, it is a plot of y versus t. So upper curve is obtained by plotting mole fraction of A in the vapor phase against corresponding temperatures. Okay. So upper curve is a plot of y versus t. Okay. Now let us move ahead. The loop curve that is formed, it divides the plot area into two regions. Which are these two regions? Vapor and liquid regions. So you can see the loop curve is dividing the plot area into two regions. So one region is lying below the lower curve, while the other region is lying above the upper curve. Okay, so that's why we are saying the loop curve divides the plot area into vapor and liquid regions. Okay, the region below x versus t curve, that is lower curve. The region below x versus t curve, it represents the liquid phase. Okay, so any point in this region, which region? The region that lies below x versus t curve. Any point in this region, it will represent a liquid phase. So if you choose any point, so it will give composition of that liquid phase and temperature of that liquid phase. Okay. Whereas the region above y versus t curve, that is this curve, the region above y versus t curve, it represents the vapor phase. Okay. So any point above the upper curve will give you vapor composition and corresponding temperature. Okay. So this region is representing vapor phase, and this region is representing liquid phase. Okay. Now let us move ahead. Now we will consider this process. We will consider a process. For that, what we are going to do, we will consider liquid solution, which is represented by any point C. Okay, so point C will be lying in the liquid region. So over here you have point C. Okay, so what we have done, we have considered a liquid solution that is represented by any point C. Okay, now we will carry out a process in which we will heat the solution. We will heat the solution, and if you are heating the solution, temperature will increase. So let us follow that process. When the solution is heated, when the solution is heated, what happens? The first vapor bubble is formed at point D. The first vapor bubble forms at point D. Now let us understand this on this diagram. So you are starting at C, and if you are heating it, the process will be followed along this line. The process will be followed along this orange line, and you are coming at this point. This point is point D. And what is the significance of this point? The first vapor bubble is formed at point D. First vapor bubble forms at point D. Okay. So the composition of the vapor that is formed over here, it is given by point E. Where is that point E? That point E is lying on the upper curve. Okay. You just understand the significance of these 2 points. So in the heating process, first vapor bubble appears at point D. Its composition in the vapor phase, it is given by point E that is lying on the upper curve. Okay. So the composition of the first vapor bubble, which is formed at point D, it is given by point E. Okay. So now at point D, since you have first vapor bubble over there, you have the liquid phase. So at point D, liquid and vapor phases, they coexist. Vapor and liquid phases, they are coexisting, and if they are coexisting, that means they are in equilibrium with each other. Therefore they are in equilibrium with each other. Okay. So what is the process? We have considered liquid solution at C, and we are heating it. So temperature will increase along this line, and at point D, the first vapor bubble will appear. Its composition is given by point E, which is lying on the upper curve. Okay. So now at point D, you have liquid and vapor phases that coexist, and therefore they are in equilibrium with. Okay. So at point D, vapor and liquid phases, they are coexisting, and therefore they are in equilibrium with each other. Okay. Now let us move on. Okay. So now once we have understood the significance of point D and point E, now we can say point D and E respectively represent liquid and vapor compositions. Point D is representing liquid composition, whereas point E is representing the vapor composition that is present in the mixture. Okay. So point D and E respectively represent liquid and vapor composition. These are equilibrium compositions. Why they are equilibrium compositions? Because liquid and vapor phases, they are in equilibrium with each other, and their compositions will be equilibrium compositions. Okay. Thus, if you talk about line DE, if you talk about line DE, endpoints, thus for the line DE, endpoint represents equilibrium compositions, and that is why line DE is called as a tie line. So you please remember, a tie line is that line whose endpoints represent equilibrium compositions. So in this case, endpoints are representing compositions of liquid and vapor that are in equilibrium with each other. Okay. So therefore, this line DE, it is called as a tie line. This is called as a tie line. Okay. What else we have to know? Once you have understood what is a tie line, you also have to remember there are infinite number of such tie lines. There are infinite number of such tie lines on this diagram. Okay. So tie line, you have understood, we have understood, and we have also understood that there is an infinite number of tie lines on this particular loop curve. Okay, now let us move ahead. The lower curve. Now let us talk more about lower curve, which is the lower curve x versus t. The curve that is obtained by plotting liquid phase compositions against corresponding temperatures. So this lower curve actually is a collection of points like D. Okay, so there is an infinite number of points like D on the lower curve. We have already understood the significance of point D. Okay, so the understanding is lower curve, that is x versus t curve, it is a collection of points like D. What is the significance? At each of these points, at each of points like D, the first vapor bubble is formed. The first vapor bubble is formed. Or we can say that the boiling process starts at each of these points. And that is the reason. Therefore, the lower curve, that is x versus t curve, it is called as the bubble point curve. The lower curve, we call it as bubble point curve because at every point on the lower curve, the boiling will start at the given composition, and therefore the lower curve is called as the bubble point curve. Okay, so let us move ahead. Further, after reaching point D, if you continue heating beyond point D, what happens? Let us see. As heating is continued beyond point D, what happens? The last drop of liquid vaporizes at point F. So the heating process is continued. You can follow it on the orange line. And the temperature rises and you arrive at this point. This point is point F. And what is the significance of point F? The last drop of liquid vaporizes at point F. The last drop that is left, it gets vaporized at point F. Okay. Now that the composition of this liquid drop, it is given by point G. So the last drop that is vaporized over here, its composition is given by point G. The composition is given by point G. Okay. Therefore, if you talk about point F represents vapor liquid mixture. Okay. So here vapor and liquid phases, they are coexisting, and therefore since they are coexisting, they are in equilibrium with each other. Okay. So point F also represent, or at point F you have vapor liquid mixture, that, or in other words, vapor and liquid phases that are coexisting, and therefore they are in equilibrium with each other. Okay, now let us continue. Okay, so once you have point G and F, again for those 2 points you can say it like this. Thus point G and F respectively represent liquid and vapor compositions. These equilibrium compositions, or these compositions are equilibrium compositions because they are representing compositions of liquid and vapor that are in equilibrium with each other. Okay. Therefore, again, line GF is a tie line because it has endpoints which are representing equilibrium compositions. Therefore, line GF is a tie line, and it is one of the infinite number of tie lines that lie on this bubble, on this loop curve. Okay. Then if you continue heating beyond point F, what is going to happen? It produces vapor at EH. Okay. So if heating is continued beyond point F, you reach this point, and this point is point H. And what does H represent? H is representing only vapor phase. H is, or at H you just have only vapor phase. You just have vapor phase. Okay. So you started with liquid solution at C, and you ended with only the vapor phase at point H. Okay. Now vapor if you follow the reverse process, you start with vapor at point H and you cool it. That means you decrease the temperature. If you do that, what happens? A reverse process occurs. Reverse process. Whatever was seen in the heating process, the reverse of that process occurs. All, you can say, events occur in a reverse order in that case. Okay, now let us understand how it occurs. So if you are cooling, you start at H, you go on cooling it, that means the temperature is reduced, you reach point F. And what happens at point F? The first drop of liquid is formed at point F. Okay. Now composition of this liquid drop that is formed at point F, it is given by point G. Okay. And you have then the tie line FG. I have already talked about it. Okay. Now the upper curve, what is that curve? Y versus T. This upper curve, it is collection of points like F. Okay. So there is an infinite number of points like F on the upper curve. And what is the significance of each of these points? At each of these points, the first drop of liquid is formed, or the condensation process starts at each of these points. The condensation process starts at each of this point, and therefore the upper curve is called as the dew point curve. The upper curve is called as the dew point curve. The upper curve is called as the dew point curve. Okay. So again, I have rewritten those points. At each point on the upper curve, the first drop of liquid is formed. The process of condensation starts, and therefore the upper curve, that is y versus t curve, it is called as the dew point curve. Okay. Every point on a tie line. Now if you talk about it, about any tie line, let us say tie line DE. If you consider any point on this line, what does that represent? At and every point on the tie line, it represents an equilibrium vapor liquid mixture. That means every point on the tie line, you will have a two-phase mixture. Vapor and liquid phases will be coexisting, and since they will be coexisting, or since they are coexisting, they are in equilibrium with each other. Okay. So I have shown point I over here. So point I, at point I, you have two phase mixture, liquid and vapor phases, they coexist and they are in equilibrium with each other. Okay. So while understanding this entire diagram, what we have observed, it is observed that the original liquid solution at C, the original liquid solution at C, it has boiled over a temperature range. There is not a single boiling point. The boiling process is starting at point D and it is finishing at point F. That's why we are saying that the original liquid solution at C, it has boiled over a temperature range. Okay. The boiling process started at D and it ended at F. Okay. So the entire boiling process is represented on this diagram. We have represented the boiling process on this diagram, and therefore this diagram is also called as the boiling point diagram. It is also called as the boiling point diagram. Okay. So it gives information about how a liquid solution boils over a temperature range. Therefore this diagram, it is also called as boiling point diagram. Okay. Now then after that, the next thing that I will be discussing over here is we will see what is the effect of increased pressure. Okay. So we have studied constant pressure equilibria. That means VLE at one constant pressure. Now we will see what happens if you increase pressure. So for example, if you are studying at 1 atmosphere, you draw of the boiling point diagram. Now if you increase the pressure to say 1.5 atmosphere, then what is the effect on the boiling point diagram? What is the effect on the loop curve? Let us understand that. Okay, so we are understanding effect of increased pressure on the boiling point diagram. On the boiling point diagram. It is boiling point diagram. Okay, so effect is discussed for again binary mixture of A and B. Same thing. A is the more volatile component. Again, this is this is a kind of revision to you. If the intersection between constant pressure plane and double surface, that means if a loop curve it is, if loop curve occurs at increased pressures, so if the intersection between the constant pressure plane and double surface which has produced the loop curve, if it occurs at increased pressure, what happens? The loop curve that is obtained through intersection of these two, you can say, entities, constant pressure plane and double surface, the loop curve, it occurs at higher temperatures. The loop curve is formed at higher temperature. This is first effect. So as you increase the pressure, loop curve will be formed at a higher temperature. If you increase the pressure beyond that, loop curve will again be formed at a higher temperature. Okay? So if the intersection is occurring at increased pressure, or simply if pressure is increased, the loop curve occurs at higher temperatures and it becomes narrower. The other effect that is seen on the loop curve is the loop curve becomes narrower. There are two effects. One is the loop curve occurs at higher temperature, and the second effect is it becomes narrower. Okay. Now in this process, you are increasing the pressure, and if you have a pressure that is greater than critical pressure of one of the component, either A or B, in this case, if the pressure becomes greater than the critical pressure, what happens? The loop curve will no longer exist and distillation is not possible in that case. The loop curve will no longer exist, or the loop curve will not exist above pressure or above critical pressure of either of the component. Okay. Okay, now let us see the effect on the diagram. So you have this plot temperature versus composition. X is equal to 0 pure B, X is equal to 1 pure A, and you are increasing the pressure. How is the pressure increased? Let the pressure be increased from P1 to P5 in this way. So P1, P2 is greater than P1, P3 is greater than P2, P4 is greater than P3, and finally P5 is greater than P4. So you will have loop curve at P1, and if the pressure is increased to P2, the loop curve will occur at higher temperature and it becomes narrow. If you increase the pressure to P3, again the loop curve occurs at a higher temperature and it becomes narrower. P4. Now P3, let us say that P3 is critical pressure of A. So above P3, you can see the loop curve is no longer existing. You cannot call this as a loop curve because it has separated from the temperature axis. Okay, so loop curve is no longer existing. If you increase pressure beyond that, again the loop curve becomes narrower. Now there will be no loop curve as such. Okay, so above the critical pressure of A, which is P3 over here, P3, this is P3, just a minute, I'll make it P3, 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 which is critical pressure of A. What happens? The loop curve is no longer existing and separation by distillation is not possible in that case. So if we have this loop curve detaching from the temperature axis, then there will be no loop curve as such, and in those cases separation by distillation it is not possible. Okay, so with this I end my discussion on this part of VLE. So in this I have talked about constant pressure equilibria. In the next lecture I'll be talking about constant temperature equilibria. Here we have understood the boiling point diagram. Boiling point diagram is nothing but the constant pressure equilibria. Then we have also understood the effect of increased pressure on the boiling point diagram. Okay, so thank you for watching my video. You please subscribe to my channel, hit the bell icon, tell all your friends to join, subscribe to my channel. We will be having more lectures on distillation. Okay, so thank you for being with me for today.